Hi everyone, today we will be doing this problem called Transceivers. This is from POI 2018 round 2 day 2. Here it is given that there are many towns and villages along a straight line which we basically identify with a number line. So town I is given a number I. Now there are multiple stations placed at various locations on a number line. So each of this is called a transceiver. A transceiver is characterized by a pair of numbers S and A with the following meaning. The signal strength at point X, where the base is located, is S. The signal strength decreases linearly as one moves from the base station and equals max 0, s minus a into d at distance d. Now we assume that the effective signal strength at a given point is the sum of signal strengths from the base station. The program should allow the operations of erecting and removing a base station as well as to query for the average effective signal strength over all integers in a given interval. So essentially in each update operation, we are given either XSA, which means that at station X, build a transceiver characterized by S, A with the following meaning, with the meaning that was given here. So this formula. And then we can remove a station that was placed at X at a previous point, and we can be given X1 and X2 where we have to find the average signal strength in all the points from x1 to x2. So average is just sum over all the signal strengths divided by the length. Now let's look at the constraints. So first subtask is n, m less than 2000. The rest of the subtasks, there are multiple subtasks. Overall, we are given that n is less than 300,000, m is less than 500,000. So n is basically the number of stations and m is the number of operations. Rather, n is the total number of such villages and towns, not the number of stations. So we have to give the corresponding answer in the query rounded down. This is not a problem. So essentially we just have to find the sum of signal strengths, or rather sum of effective signal strengths in the region x1 to x2. So let's look at what this effectively corresponds to, what the formula corresponds to. So let's say this is the number line. There are multiple towns here. Now you place a station somewhere like this. And this is also a valid town. Now the signal strength here is S. Let me go back. Yeah. So the signal strength here is S. Here at this point it is S minus A. At this point it is S minus 2A. At this point it is S minus 3A. Here it is S minus 4A. Dot dot dot. Let's say S equal to S is less than, let's say, 7A. Then we continue 4A, 5A, 6A. But here if we do S minus 7A, this would be actually lesser than 0. So here instead of it being a negative number, we just replace it by 0. And similarly in this side also, this is S minus A, this is S minus 2A, S minus 3A, and so on up to S minus 6A. So 3A, 4A, 5A, 6A. There in at this position it won't be S minus 7, it will be just 0 and 0, so on. So for this tower we have a contribution curve like this. I mean, it's obviously you are just looking at particular points on this sloped line. The slope of this line is essentially minus A, and there is a similar sloped line like this, and you are considering only these points. So for now what I have shown is the contribution for a particular tower over these regions. Now there might be multiple towers. So there might be a tower here which also has a sloped line like this, and something here also. There can be a tower like this which has a, let's say, slope like this. So this slope is determined by A. This tower length is given by S. Now for every index, we just have to find the sum of the contribution of each of the tower ranges. So this tower contributes something, this tower contributes something. This tower, it does not contribute something negative, it just contributes 0 all the way. So it's just 0. So we just have to count what is the contribution of every one of them and take the sum. So what do we do here? This effectively is exactly the same as adding an AP. So same as adding an AP to kind of both the directions. So you are kind of adding an AP in this region, you are adding an AP in this region. So constraint is that no term becomes 0, and there is a particular starting point. So basically we can incorporate this into saying that, okay, so add this AP in a particular range. So let's say the AP started from somewhere here, and then you add to all of them the corresponding value of the AP. Now for the first subtask, as we were given n comma m less than equal to 2000, we could have just for every query updated each of the positions individually in the AP, and it would have cost us order n into m time. But in actuality, we are given n equal to 3, 5 and m equal to 5e5 for the entire problem. Now let's further break this down into what are we actually adding. There is an AP like this where we are given a certain first term and we are also given a difference value. So this is the first term, this is the diff value. For here it's kind of the reverse. So the first term is the same but the difference value is kind of reversed, or rather we can think of it as the first term is here and we are adding difference value like this every time, and it continues till some point. Now the hard part is, so how do we kind of try to attempt to do this problem? Well, this is doable using a segment tree, but how exactly? What if we can store in the segment tree some data like this, the first term let's say and the difference, and how we do this in a segment tree is, instead of saying that we want to do a range update like this where we are, so this is let's say the segment tree and we are trying to update this range with this particular AP, and I'm drawing this as a slanted line because as a line is like y equal to mx plus c. Similarly the term ti of an AP is equal to let's say d into some x which is the xth term, so tx equal to dx plus uh, s, something like this, right? I mean it's not exactly this formula but it kind of corresponds to that, so I am drawing it as a line. So we are adding this AP in a range, right, in our problem. But what is much easier to do is just say that, okay, let my AP start here, and instead of it ending at this position, let it continue till the end, till infinity. Now how can you make a range AP using this infinity APs? Well, you can just start another AP from here. So this was the length here, right? So you take the negative of that and make a AP like this. So basically this and this cancels out and you just have the sum of this AP. So effectively for every AP, in range let's say x to y, break it into two APs, one from x to infinity and one from y plus 1 to infinity. Now obviously we are not going to extend it to infinity, we are only going to infinity. In our case is just max n, right? Now how does that help us, or rather how can we do the lazy propagation that is needed for this problem? I mean, you are doing a range update, so you need some lazy propagation, but what do we exactly do? First, note that APs are addable. What do I mean by that? Let's say there is an AP of S1 plus A1n, which gives the term for Tn for the first AP, and there is a second AP which is S2 plus A2n. If we want to find the sum of Tn, so let me call this Tn1 and let me call this Tn2. If we want to find the sum of Tn1 plus Tn2, all we have to do is S1 plus S2. So this becomes our new S. So new S plus we have to do A1 plus A2, right? We are just adding these two equations here. But this we can write it as a new A into N. So this is a new AP, right? This is also in the form of an AP. So this is what I mean by APs are addable. So this kind of hints towards a possible lazy propagation technique. Here's how we can do it. Let's say at a particular node, we know what the first term and the difference term are, and we want to lazily update the two children. Now one thing to note is, what is the sum of all the nodes in this particular range? That is given by sum equal to 2 into ft plus n minus 1, where n is the length of the range, into diff whole into n by 2. This is a standard AP sum formula. If there are n numbers with ft being the first term and diff being the difference term, we can easily find this. Now how do I update my children? Well, we essentially want to find the first term and the diff here, and the first term and the diff here. For the left child, you can just add to the first term and diff variable of this child the lazy values from here. So this is just you add the lazy values here. For this, the difference value is the same as this difference value, but the first term is different. Why? So let's say here there were x elements, then the first term here will be equal to x into diff. Note that when I say diff, I mean the lazy diff here, and let me call this ft1, so plus ft1. This is the ft value for this right child. Does that make sense? I mean, here there was some AP. When you are breaking it into left and right child, you are just breaking it like this. So for the left child, this part is okay. The first term is correct. The difference is basically corresponding to the slope, which is also correct. But for this term, this right child, the slope is correct, which means that the difference value is okay. But the first term has actually increased, and it has increased by how much? It is effectively diff plus last element here, which effectively corresponds to this. So this is how we update our segment tree when we are adding an AP. So essentially, just to reiterate, for every segment tree in a node, we store 4 data values: first term, diff term, and then the lazy versions of them. So after we update the node using the lazy values will become 0, and the first term and diff value will effectively correspond to what is the overall AP at a particular region, and we can get our answer. So how do we get our answer? Well, when we do a lazy, we know that if both of my children have been updated, then my answer is just sum of the two children, right? If they are not updated, that means I currently possess their previous sums as well as what my lazy value added to my sum. So that is hopefully standard lazy propagation. Now, how do we break our queries into APs which we can then insert into our segment tree? Well, we characterize an AP using its first term and its difference term, right? So when we are given a particular point in our query, this is not the first term. I mean, this is the first term for the AP of the right side, but then you have to add an infinite AP here. You have to add an infinite AP like this. So let me use a different color. So you have to add an infinite AP like this. Then you have to add an infinite AP like this, and you have to add an infinite AP like this. Why so? The red portion and the blue portion cancel out after this point, and the dark blue purplish portion here. So effectively this portion cancel out with this portion. So you are just left with this region and this region, just as you wanted. So effectively every update operation corresponds to 4 AP additions. Note that you have to handle it carefully, because if this left endpoint is actually lesser than 0, so let's say this was 0 and this was the left endpoint, then you actually want to start your AP from this point onwards and not from a negative index, because your segment tree does not support negative indexes. And this is effectively the entire problem. This problem just corresponds to whether you can add AP to a range or not. To reiterate, we did the following things. We reduced that adding AP to a range, add AP to x comma y, reduced to adding AP from x to infinity, and y plus 1 to infinity. We saw that to add a range in a segment tree, we have to store first term and diff term and their lazy values also. To update a node with the lazy first term diff terms, you can use the sum of AP formula, which uses these two values, and then to push them to the child, the left child and the right child. For the left child, you can directly push first term and diff term to its first term diff terms, and for here you can push the diff term right now, but for the first term you have to kind of recalculate the first term based on the first term here and the size of the left child. If you can do that, you can get the first term here, the diff term here, and you can effectively add the AP here also. Note that when I'm saying that adding the first term, adding the diff term to the two children, I mean that you add the lazy first term variable and the lazy diff term variables. Let's look into the code for this. So this is our segment tree. Push down function means you are pushing down the lazy values. So when you push down at a current node, you basically calculate the values for the current node. So for the first term, you add the lazy first terms. For difference term, you add the difference terms from lazy. Then you update its children. For the lazy first term of the left child, you can just keep the first term there. For the lazy first term of the right child, you have to add lazy difference of your current node into the size of the left child to the first term of your current node. for that particular AP. For the difference terms, you can just add them as is, and then you set your own lazy values to 0 and add y to your answer, which is st node. Y is the contribution of the AP that was stored in your lazy variables, because that AP is not contributed by the sum of your left and right children till now. So that is what you do in the push down. However, once you update your left and right child, that means your own lazy values are null and void. Your left and right child have already been updated, so you can just combine their values and add it to your own node. For a get function, we do a similar thing. Add AP is a helper function which effectively adds the AP characterized by start term S and difference term A to the range X to Y, and the rest of the code is just handling the input and calling add AP as appropriate. So this was the solution for the problem transceivers. Hopefully you like the problem. So that's it for today. Thank you.